Imagine a catastrophe that outruns its own alarm bells. In the deepest fears of seismologists lies a phenomenon that sounds like science fiction. Earthquakes that travel so fast, they overtake the very seismic waves meant to warn us of their arrival. These are supershear earthquakes, and they represent one of the most underappreciated threats facing California today. The mechanism defies intuition, violating what many assumed were fundamental limits on how quickly rock can fracture. When a typical earthquake ruptures along a fault, seismic waves radiate outward like ripples in a pond, providing precious seconds of warning before the most destructive shaking arrives. The rupture front travels through Earth's crust at speeds slower than the shear waves it generates. But supershear earthquakes shatter this pattern entirely. The rupture accelerates beyond the speed of seismic shear waves, typically exceeding 3 kilometers per second, and begins generating something far more terrifying, a Mach cone. Just as a supersonic jet creates a thunderous boom when it breaks the sound barrier, a supershear earthquake produces concentrated shock fronts that amplify ground shaking to devastating levels. The seismic energy piles up into a narrow, high-amplitude beam that travels ahead of the rupture. Researchers describe this as a double strike. First comes an initial sharp jolt, followed immediately by trailing waves of intense shaking. The result is destruction spread across far greater distances than conventional earthquakes of similar magnitude. For decades, scientists believed supershear earthquakes were exceedingly rare anomalies, curiosities that appeared perhaps once or twice per century. Recent global analyses have demolished this assumption. Research examining magnitude 6.7 and larger strike-slip earthquakes between 2000 and 2020 revealed a startling statistic. Approximately 14% of these major temblors achieved supershear speeds. That figure is more than double previous estimates of roughly 6%. Globally, about 1 in 3 major strike-slip earthquakes qualifies as a supershear event. This matters enormously for California, where 70% of the population lives within 30 miles of an active fault. The San Andreas Fault system, stretching roughly 800 miles through the state, fits the geological profile of a supershear candidate almost perfectly. Long, straight, mature, with sections that have remained locked for over a century, while stress accumulates relentlessly. Faults with simple geometry and few large bends allow rupture energy to concentrate rather than disperse. When these faults remain locked for extended periods, the accumulated strain provides the explosive potential needed for rupture to accelerate to supershear speeds. The San Andreas Fault has not produced a major earthquake in Southern California for over 300 years along its southern section. This far exceeds the historical average interval of approximately 180 years. This extended quiet is not reassuring. Geologists describe the fault as locked and loaded. The current hiatus has allowed stress to build to extraordinary levels, and when release finally comes, the conditions strongly favor rapid, violent rupture. Evidence suggests that the infamous 1906 San Francisco earthquake was itself a supershear event, with rupture propagating along approximately 310 miles of fault at speeds exceeding normal shear wave velocity. That disaster killed over 3,000 people and destroyed more than 80% of the city. California can expect multiple magnitude 7 earthquakes in the coming decades with complete certainty. The question is not whether they will occur, but whether any will achieve supershear speeds. Given the 1 in 3 global probability, the likelihood is substantial. The destructive potential of supershear earthquakes was demonstrated with horrifying clarity in recent years. In February 2023, a magnitude 7.8 earthquake struck southeastern Turkey and northern Syria, killing at least 56,000 people and leaving millions homeless. Analysis revealed the rupture transitioned to supershear speed, approximately 19 kilometers from the epicenter. The intense ground motion contributed to catastrophic building collapses across 11 provinces spanning an area roughly the size of Germany. The phenomenon repeated itself in March 2025 when a magnitude 7.7 earthquake devastated central Myanmar. The rupture extended over 450 kilometers along the San Andreas Fault, sustaining supershear velocities of up to 5.3 kilometers per second. This made it one of the longest and fastest earthquake ruptures ever recorded on land. Over 5,000 people perished. The Mach cone effect transmitted damaging seismic energy over 1,000 kilometers to Bangkok, Thailand, where buildings swayed and collapsed. Both events shared characteristics alarmingly similar to California's geological setting: mature strike, slip faults with simple geometry, long periods of stress accumulation, and dense populations living near the fault traces. Current California building standards and hazard planning contain a critical blind spot. Infrastructure and buildings are generally engineered to withstand the strongest shaking perpendicular to faults, reflecting the expected behavior of conventional earthquakes. But supershear quakes direct their destructive energy along the fault line itself, fundamentally changing the geometry of destruction and the forces buildings must resist. Critical structures remain unprepared for this directional force. Denser seismic monitoring near major faults would improve scientists' understanding of where and when supershear ruptures could begin. Advanced computer simulations modeling supershear scenarios can inform engineering guidelines and help identify which structures face the greatest risk. The good news is that preparation remains possible. Understanding which faults possess supershear potential allows targeted infrastructure improvements before disaster strikes. Early warning systems can be calibrated to account for the compressed timeframes supershear events create. The science exists to confront this threat. What remains is the collective will to act on knowledge before the next great earthquake puts California's readiness to the ultimate test. As we've seen through these examples, understanding complex phenomena, from the terrifying reality of supershear earthquakes to mastering seemingly daunting tasks, is within everyone's reach, with clear explanation and accessible visuals. The images we explored showcased a world of potential danger and opportunity, highlighting how critical it is to grasp even the most specialized knowledge for safety and progress. We've touched on the sobering implications for regions like California, emphasizing the need for greater awareness and preparedness in the face of these powerful natural events. Thank you for watching. If you found this exploration insightful, please give us a like and share your own experiences or hidden gems in the comments below.